We are going to go over trig derivatives, okay? So there's a big memorize thing right here. So these are the 6 trig functions: sine, cosine, tangent, cosecant, secant, and cotangent, and their derivatives. So the derivative of sine is cosine, derivative of cosine is negative sine. I remember that with sine can go to cosine, so I think of that as like going forward, and then cosine to sine is going backwards, so it has to be negative if you go backwards. That's in my brain. That makes sense. If that messes up your brain, ignore that I said that. And then tangent is secant squared. Cosecant, this is wrong on your notes. It says cosecant tangent. Is that right on your notes? Scribble that out and write cotangent. I forgot to change it. So the derivative of cosecant should say negative cosecant cotangent. And then secant is secant tangent. Cotangent is negative cosecant squared. And when we get to class on Wednesday, you're going to have a quiz on this. Quiz on Wednesday of your trig derivatives. Just tell me, you'll have 6 blanks, and you'll just tell me the derivatives of each of those. That's it. That's all you got to do. Okay? So, we're going to work these. First one's easy. What's the derivative of cosine? Negative sine x, yes. Okay. This one, since there's a plus there, you can take the derivative of 5, which is what? 0. And then the derivative of cosine. Negative sine. So you have the same answer there. Okay. This one, you see the 5 is attached to the trig word. Okay. Just like me saying 5x, right? Your answer would be 5, right? You didn't do anything to the 5. You took the derivative of the x, right? Same thing here. You just leave your 5 alone. And then, again, the derivative of cosine is negative sine, so you'd bring your negative out in front. 5 sine x.
So it doesn't matter if there's a number in front?
That's right. You just treat it like normal. Okay. All right. So number 4, and I hope you can see that I'm doing something here. You see how all of these are very similar, but they're all different, except for the first 2. Give you the same number. The difference between 3 and 4 is that there is a variable in between your number and your trig word, right? So we're going to make a little note. If there's a variable before your trig word, then use product rule. Okay, because hopefully you can see that this is, I'm having to record, so I need to stay over here. Don't let me walk over there. Make me stay over here. You can see that this is one thing, one term times another term, okay? And that term is not just a number, it has x in it, right? So if we did the product rule, we would have 1, d1, 2, d2. So 1 would be 5x, and 2 is cosine x. So we'll take the derivative of both of those. What's the derivative of 5x? And then the derivative of cosine? negative sign. And then we're going to do the first, 5x, times the derivative of the second, which is negative sign, plus the second times the derivative of the first. And then all we have to do is just clean up. So we're just going to take this negative and bring it out in front. So we get negative 5x sine x. And then, of course, we'll just bring that 5 to the front of cosine. Like that. Everybody okay with that?
So you can have a variable in your derivative, but not in the first one?
Say it one more time.
So like you have, you're starting with 5x cosine x,
Mm-hmm.
but it's perfectly okay to have 5x sine x as your derivative?
Mm-hmm. Yes, okay.
If you wanted to do this, that's just taking some.
Yeah, that's okay.
It's not like you can't do it, it's just.
Yeah. We have no other choice here. It's fine that it's written like this. There's no problem with it. We just have to use the product rule to take the derivative. Does that make sense?
Okay.
Ish. Okay. The more we work them, the more it'll start to make sense. Okay. So what do we have going on here with number 5? We have sine x. That's cool. We can take the derivative of that. But then we have x cosine x. So we have to use what? The product rule. Okay. So we'll go over here. 1 is x, 2 is cosine x. So the derivative of x is just 1, right? And then the derivative of cosine is, I put 3, d2. Negative cosine? Negative sine, sorry. Okay? Then we'll take the derivative. So we will take the derivative of sine. That has nothing to do with the product rule. Everybody okay? So I'm doing this portion of it. I'm going to do the product rule with that portion. So the derivative of sine is what? Cosine. Minus, now I'm going to do the product rule. Okay? So I have the first times the derivative of the second plus the second times the derivative of the first. Okay, I'm going to clean up the blue and just write that as negative x sine x plus cosine x. So I cleaned that up because it was easy and I didn't have to write it all over again, okay? So what am I going to have to do with that negative? Out in front, the black one. Distribute it, right? So I can, bless you. So I can distribute that and then write the next line. So that's, still have cosine x, not doing anything with that. And then I have positive x sine x minus cosine x. Okay, well, I have like terms, right? Cosine minus cosine is what? 0. So I'm just left with x sine x. Okay. Next one. We'll obviously have to use the product rule here as well. I have one thing times another thing. And there's x's involved, right? Secant x, tangent x. Okay, so we'll do, the first is secant, the second is tangent. So what's the derivative of secant? Secant x, tangent x. And then the derivative of, why do I keep writing 3? It's because I'm looking at 2. Derivative of 2 is secant squared x. Right? So again, we'll do the first times the derivative of the second. Plus the second times the derivative of the first. And then we'll just clean up. So this would be secant cubed x plus, and then if I took this, this would just be, because this is one thing, right? One term. And so that's just going to be secant x tangent squared x. Questions so far? You doing okay? What do you think I'm going to do for this one? The quotient rule, right? All right, so we have low and high. I need to make my pen smaller when I do that. 1 plus tangent, and high is tangent. So the derivative of low is just secant squared, because that's the derivative of tangent, right? And the derivative of 1 is 0. And then the derivative of tangent again is secant squared. So you see that both derivatives are the same, which makes sense, right? Because you have 1 plus tangent x. Okay? So we do low times the derivative of high minus high times low, derivative of low, all over low squared okay. What do we need to do with this first part up here? Distribute. FOIL would be binomial times binomial. So we have binomial times monomial. So all you have to do is distribute. It just looks backwards. So you get secant squared plus secant squared x tangent x. And then we'll just make that negative, that second part, right? We'll just say minus secant squared x tangent x, all over low squared still. Notice anything? Those equal 0, right? So you're just left with secant squared over 1 plus tangent x squared. Feel okay about the quotient rule using trig? Okay, couple more. Okay, pi is just a number, right? It would be the same thing as if I had written 5 tangent x. Okay, so my pi doesn't go anywhere. All I have to do is take the derivative of tangent, which is secant squared, so I get pi secant squared x. That's what I have to do. Because pi is just a number. Okay? And then last one. Do we have to do the power rule or anything like that? Not the power rule, the product rule? Because it's plus, right? So you're just going to take the derivative of tangent, which is secant squared, and then you'll take the derivative of cotangent, which is, yes, but it's negative, so you'll have a minus sign. Okay? Any questions about any of those examples? Okay, this one's fun. It says prove that the derivative of tangent is secant squared. Okay, so we're going to have to do a little bit of some algebra and some trig. Okay, it's going to use some of our trig identities. Okay, so if we're thinking about tangent, okay, how can we write tangent but use words like sine and cosine? Sine over cosine. Okay. So, if we can take the derivative of sine over cosine and it equals secant squared, that would prove that tangent, because that's also sine over cosine, equals secant squared. Okay? So what rule are we going to have to do for this guy? The quotient rule? So you'll do your low is cosine, your high is sine. I don't know why I did that so close to that. The derivative of cosine is negative sine. The derivative of sine is positive cosine. So then you'll take that derivative, so you'll do low times the derivative of high minus high d low all over low squared, so cosine squared. Let me write it like this first. Okay, so we're going to clean up a little bit. That's cosine squared, and this would give you minus sine squared. And then you would distribute that negative, right? So we would get plus sine squared. And then all over cosine squared x. Yes? Okay. Do I need to go over the fact that this is not cosine x squared? Because that would be dealing with the angle, and we're not dealing with the angle. We're dealing with the trig word. Okay? What is cosine squared plus sine squared equal to? 1. That's a trig. That's your Pythagorean identities for trig. Okay? That we were supposed to know. Which gives you 1 over cosine squared. What's the reciprocal of cosine? Secant. So 1 over cosine squared equals what? which is great because that proves it. I guess it's more of a verify, but whatever. You guys feel okay about that one? This means yes, this means no. Okay. We're going to move on to some applications of these. We're going to look at derivatives as rates of change. So we're going to do some word problems, which I know you guys hate. It's going to feel very physics in here for a second. Here's the good news. I don't give you any homework on this stuff. I also don't give you any of these on your test, okay? So we do word problems later to the point where you're going to be like, calm down, okay? And you will be tested on all of that. But this is just kind of small stuff, okay? So one-dimensional motion, an object moving along a line is what I'm talking about. So in the real world, I talked about this when we first talked about derivatives, right? Everything is changing in the world. And so that's why we love to do derivatives. So this is just showing you that it is actually, like, you can use it in the real world. And then that triangle is the Greek letter delta, and that means the change in. So anytime we talk about slope, we're talking about, like if we talk about it just normal slope, it's the change in y over the change in x, right? That's how you would say it. So you could annotate that by the change in y over the change in x. Okay? And then S of t is the position function, and t represents time. Okay? So that's going to be the position of whatever we're dealing with. Most of the time it's like you're dropping something or you're throwing something in the air, something like that, okay? And we have two kinds of velocity. We have average velocity and instantaneous velocity. And anytime you hear the word instantaneous, whatever, you should be thinking derivative, right? The instantaneous rate of change. We went over that when we first went over derivative, right? But your average velocity is just going to be the slope of a line. The slope of a line formula. And the instantaneous velocity is the derivative. Okay? Most times if you see the word velocity, you need to take the derivative. Okay? So velocity, I'm reading this part over here. Velocity at time t is the derivative of that, whatever it is. Speed at time t is just the absolute value of the derivative. And then acceleration would be the second derivative. So you have velocity, first derivative, acceleration, second derivative. Okay? That's like the main thing that you need to understand. Okay? So we're going to work these. Once again, they're not a huge deal, okay? It says an object is dropped from a height of 100 feet. Its height at time t is given by that position function. Find the velocity after 2 seconds. So we are looking for the velocity at a certain instance. We're looking for the instantaneous velocity. You see? Okay? So you're going to say the velocity at time t. So we just need to take the derivative of our position function, right? Which is what? Negative 32t, right? You bring your t to the front, multiply times 16, subtract 1 off of your power, okay? Well, I want my time to be after 2 seconds, so once I've found the derivative, all I have to do is say, okay, let's plug in my time. Negative 64, and this is going to be feet per second. Feet per second. And you can make a little note. Velocity is units per second. And then acceleration, it's a long word. Acceleration is units per second squared. So whatever unit, in our case it was feet per second for velocity.
How is our velocity negative?
Because I'm dropping it.
Oh.
An object is dropped from height. We're going to work one in a second where it doesn't make sense that it's negative, and we'll have to do the positive of it. We'll see. Okay, number 2. The equation of motion for a particle is this guy in centimeters and t in seconds. So I want you to find the velocity after 2 seconds. So we're going to take the derivative and then plug it in. So the derivative of that position function is what? Minus
T squared plus
10t plus 3. 6t squared minus 10t plus 3. Then we're just going to plug in 2, right, for t? So that would be 2 squared is 4. So that's 24 minus 20 plus 3, so 7. And that's centimeters per second. Then it says find the acceleration after 2 seconds. So what are we going to do? Do the second derivative. So we're going to go over here and take the derivative of this guy, right? So we'll do the acceleration. Okay, so what's the second derivative of that over there on the left? 12t minus 10. And then plug in 2. So you get 14 centimeters per second squared. I'm running out of room. There you go. Okay? Everybody good with those? Those are pretty easy. Okay, these are a little more, they're not difficult, you just kind of have to figure out what you're looking for. So it says, suppose a stone is thrown vertically upward from the edge of a cliff on Earth with an initial velocity of 19.6 meters per second from a height of 24.5 meters above the ground. The height in meters of the stone above the ground t seconds after it is thrown is this guy. I want you to determine the velocity of the stone after t seconds. That's easy, right? You take the derivative of the position function. So we'll do the velocity, and we'll get negative 9.8 t plus 19.6. You guys have a plus right here? Not a minus, right? Okay, good. All right. So that one was easy. Then it says, when does the stone reach its highest point? So we're on the edge of a cliff, not a cliff, and we're throwing the stone in the air, right? So in algebra, what that's going to look like is if I throw it, it's going to reach a point and then come back down, right? So in algebra, we would answer it by finding the x-coordinate of the vertex of the parabola because it would make a parabola shape, right? I throw it up, It's going to reach some point and come back down, okay? So in algebra, we answer this by finding the x-coordinate of the vertex of the parabola. Of the in calculus, we can find this by, so we'll say in calculus the max height is when the first derivative equals 0. So all we have to do is set our velocity, which we know that, right, equal to 0. And that would be the time that it hit the ground. So we would just need to say our velocity, which we have right above it, right? Equals 0. And this makes sense, right? Because a derivative is the instantaneous rate of change. So we just want to know at the instant where it is 0, because it would be 0. It's not moving anymore, right? We just want to set it equal to 0 and find it. That's how we would do that. So this is just a normal, real easy equation. We would subtract 19.6, and then what? Divide by negative 9.8, and get what? 2 seconds. Everybody okay with that? Yes, no? Okay. Then it says, what is the height of the stone at the highest point? So we already know when it reaches the highest point, okay? But if we're looking for just the height of the stone at the highest point, this is looking for position. Looking for position. So we're not going to use a derivative, right? That wouldn't make any sense. We just want to know the position of it at the highest point. So that would be is t. I'm just going to write the position function. I'm having to look. T squared 19.6 t plus 24.5. Okay. Well, we have to know what t is at the highest point. What is it? What? 2, right here. We already found it, right? We know when the stone reaches its highest point is at 2 seconds. So the height of the stone at its highest point would be us just plugging in 2 for t. So that would give us 44.1 meters. Okay. Then it says, when does the stone strike the ground? Okay, so the stone strikes the ground when the position function is 0. Right? So all you would have to do is set the position function. So I'm going to write that out again. Plus 19.6 plus 24.5 equals 0. So I'm just taking my position function and setting it equals 0. Okay, well, this would be, if we're thinking like algebra-wise, this is just a quadratic, okay? And you can take out 4.9 from all three terms. That would take you a second to figure out, okay? So you're left with t squared minus 4t minus 5 equals 0. And then I can factor that on the inside. Different signs, 5 and 1, right? Yes? And then set them equal to 0. And then we're looking for when the stone strikes the ground, okay? So it makes no sense for that time to be negative, right? Conceptually, that doesn't make any sense. So we're going to choose this one. Because we can't have negative time. Makes no sense. Okay, and then look at that question and then the next one. With what velocity does the stone strike the ground? Do you see the difference? You see, that's why we used position here, and why we'll use velocity, the first derivative, here, okay? So we already have what the velocity is of our function, negative 9.8 t plus 19.6. We found that at the very beginning. And then what are we going to plug in for t? 5, yes. Negative 24.4 meters per second. And then why does it make sense for the velocity to be negative, but it didn't make sense over here?
It's falling.
It's falling, yeah. We were looking for a specific, like it was, when does it strike the ground, the position of it, but the velocity when it struck the ground would be negative because the stone was falling. Okay?